I'm working in an area of precision animal management or precision livestock farming. Those terms are interchangeable. I'm going to start with a definition of what that is. That is developing tools to utilize real-time data on individual animals to aid in management decisions. There are a few really key words in there. First of all, it is a tool. We will not replace animal caretakers. That is never our goal. Our goal is to help make animal caretakers much more efficient and time management wise. The next key word is real-time data. What I'm going to show you today is old data, but what our goal is to collect the data, analyze it, and then put management decisions on a continuous basis, whether that is by hour or by day. On individual animals, and I put that in quotes, you know, when we're working with dairy, we are already there. Dairy cows are individuals. We're tagging them. We're collecting data on individuals. We're there in sows as well. We are working towards getting there in finishing pigs and broilers. We have job security for a long time for broilers. So bottom line, we're going to use data to help drive decision making. Like I said, when we collect these data streams, we can use those data streams for 3 different purposes. We can use them for precision livestock farming or precision animal management. As researchers, we are always pushing the envelope. We're always looking for new ways. Some things aren't going to work, and that's okay, but that's what we do. We just check it out, make sure it will work. Industry will pick it up and make a product. The next thing is we are seeing animals within their environment in a way we've never been able to see before. Therefore, we can understand how many feeder spaces they need. We can understand how pigs are utilizing the space that they're given. We can understand how cows are using the space that they're given in the freestall barn. So we can use that information to improve pen design, to improve animal enclosures in general. The third thing we can use these data streams for is developing unique phenotypes. Mostly behavioral phenotypes is what we are looking at, using vision and RFID to do those. So I'm going to back the train way up, and we're going to start with sensor systems. I'm going to talk through some definitions and some ways that we can assess error. So precision and accuracy. Sometimes people use those interchangeably. They are very much different. They are 2 measures of observable error. Accuracy is how close our measurement is to the actual measurement, the actual reference measurement. These are systematic errors, and you can think about them as statistical bias, and these values are published. So you can, and I'll show you some examples later. You look at a temperature sensor and it'll say it's within plus or minus 0.1 degrees C. So those are published, and you can select sensors based on those. When we look at precision is how close the readings are to each other. So these are not published. You have to determine these experimentally. They are random errors. So you can think about it as statistical variability within the group of measurements. And this, like I said, is not a published value. So to give you some examples of what I mean, I have a few graphics. So if a sensor has very high accuracy and very high precision, they are always very tightly in a group and right on the target value. When we have high accuracy but low precision, that means the average meets the target very closely, but we have a big scattering of points. So each individual point might have a lot of error associated with it. When we have high accuracy or low accuracy and high precision, they're tightly grouped together, but they're not on target. So this is a systematic bias that we have. And then we have sensors that are not very accurate and aren't very precise. So you have a scattering of points that aren't close to the average. If you want to look at these terms in statistical ways, you can look at it this way. So let's see, oh, it does work. Okay, so here would be our reference value, or the value that we want to achieve, or that our standard is telling us. This is what our sensor is telling us. So our accuracy is how far off we are. The precision is this normal distribution, or that width at the bottom is our precision. Resolution is different. Resolution is the smallest change a sensor can detect. This is a published value. You can find resolution. And a lot of people get confused with resolution and accuracy. For example, a sensor might give you a body temperature of 37.1 C, or a sensor might give you a temperature reading of 37.0625. Both of them have the same accuracy. It doesn't mean that the one with more decimals is a better sensor or more accurate. It has more resolution, so you can see smaller steps. So when we get sensors, we can do a calibration on sensors, and the calibration can correct those offsets in accuracy. They're not going to change your precision. So if you have a scattering of points, you're going to have a scattering of points. It's just going to be more accurate. It's going to be closer to that value. And you cannot correct precision issues. Yeah. So, for example, if you calibrate a temperature sensor, you take a series of temperatures and you record it with a thermometer, and you record it with your sensor. You're aiming for a slope of 1 and an offset of 0. And so this one would be very close. It would be an accurate and precise sensor. Here we have a sensor that is very precise, but has an offset of 2.5 degrees. So this one you can easily calibrate to pull that back down to make it very accurate and precise. In this case, we might have an accurate sensor, but we don't have a very precise sensor. We don't have an accurate or precise sensor. We can do a calibration. It will help improve its accuracy, but we still have a lot of scattering around that point, so it's not going to improve it completely. So then I was going to help you, or go through a couple examples of sensor selection. So I picked I button because an I button is a fairly universal temperature sensor, and it's been used in a lot of different studies. And you can see that the price range on them goes from 37 to 175. So what are you getting for your money, and how do you decide which of these sensors you really want to look at? So we're going to take the $47 one. So the first thing when we select a sensor, we want to make sure that it's within the range of temperatures that we want to select. So say we want to do body temperature. So our range for the sensor is -40 to 85 degrees C. So it's definitely within the range of body temperature. Our accuracy is ±1 C. I would say this is not usable for body temperature. And our resolution is 0.5 C. So all you're going to get is 37.5, 38, 37, right? There's not going to be anything else in between there. The other thing to look at, especially in these self-contained sensors, is how much data they can hold. So this small sensor can hold 2048 values, logging, and it doesn't matter. And it can log from 1 minute to 255 minutes. So if you log it at 1 minute, you can get little less than 1 day's worth of data. Or I guess you can get almost 2 days worth of data, sorry. So now we're going to look at the $103 sensor. It has the same temperature range. So it's between 40 and 85. The accuracy is still the same. So plus or minus 0.5. Oh no, the other one was 1, and this is 0.5. So it's a little bit more accurate, but still, if you want body temperature, this probably isn't the best sensor for you. And then the resolution, this resolution, you can change the resolution. If you want more values, you can leave the resolution at 0.5. And so that's using 8-bit resolution. If you move to 11-bit resolution, you get a lot more resolution, but you limit the number of points you can store. So how do you know how frequently to take data? And I'm going to use body temperature as an example. So sampling frequency is the number of samples per unit time. And when we talk in engineering, we usually use seconds as our time unit. So we talk about 1 hertz, and that's 1 sample per second. In animal stuff, like, we don't necessarily collect data at 1 hertz all the time. So how do we determine how much data we want, and how does that look? So if you go back to engineering basics, they will tell you, ideally, you want to sample 10 times the frequency of occurrence. So thinking about body temperature, we have a diurnal effect, so we have a 1 day. So ideally, we would need to collect at least 10 times that amount of data. Minimally, we need to collect 2 points, so we understand the variability. So going in body temperature, what sensors should we select? And how do we decide that? So of course, size is very important, right? We need the size appropriate for the animal. We need to know the temperature range and make sure that it's within the range of the sensor. And if we can get it tight to the body temperature range, that is ideal. We need to know the accuracy, the resolution. We can figure out the precision, but we can also, we need to understand how much data that little sensor can hold. So this is a sensor that we have used for a lot of years, and it's a hobo onset water temperature probe. So the accuracy is plus or minus 0.2 C, so that's not too bad. And it can store 42,000 points. So we can get quite a bit of data at even 1 minute data selection. We look at eye buttons, and like I showed you earlier, the cheapest eye button is plus or minus 1 degree C and can store 2,048 samples. So depending on what you're doing, that might be okay if you're doing just environment. If you're doing body temperature, you probably want something a little bit more accurate. And then here's another one that I haven't used, but I'm very intrigued by, and that is Micro T by Star ODDI. Maybe somebody has used this one. The accuracy is incredible, 0.06 C, and can store up to 65,000 data points. So this one would be really interesting to try in different animals or different experiments. So frequency of measurement, 1 minute, 1 day, twice a day, 1 hour. How do we decide? And like I said, there's a diurnal effect, so 10 times would be good, unless you want to look at small changes within the day, and then you have to increase that sampling. So here is a data set that was collected on a heifer using the water temp probe. If you see those little square edges on there, that is showing you the resolution of the sensor. So those are the small steps that it can record, right? And this data was collected at 1 minute during the entire day. Do we need 1 minute data? There's a lot of variability there that we can look at. It depends on our study and what we want to get out of the study. If we look at twice a day, those are the values that we're going to get. So we are losing a lot of information if we only record twice a day, but it might be okay if we're just looking at average body temperature over a long period of time. If we look at every hour, the green line shows us what it would look like if we just took a point every single hour. So we capture a lot of the variability. So, and this would be 20 times that diurnal effect, right? And this one is every 15 minutes. So we don't actually gain a lot from every hour to every 15 minutes. We gain a little bit of the variability in there. How much do we lose by not doing it every minute? It might be okay to go every 15 minutes. It makes our data, our little data logger last a lot longer, can record a lot more data. So as you're setting up experiments, if you're anything like me, more data is always better. So I always want to collect as much data as possible, but we need to think through and make sure that we're actually collecting the data that we need. SAS is not going to handle 1 minute data over a 3-month period. You can overwhelm SAS in a hurry. So you might end up reducing that to every hour anyway. Are there other things that you can look at, like fast Fourier transforms, looking at some of the frequencies within there? That might be interesting. So think about what you're going to do with the data before you decide how frequently to collect that data. So then I also wanted to point out there's a lot of different methods, and I'm using body temperature as my reference or as my example, but understand it doesn't matter what we're talking about. There's a lot of different methods of using it. So we need to understand the different methods, and we need to pick the appropriate method. So with body temperature, there has been a lot of different ways to monitor body temperature. Rectal temperature, vaginal temperature, rumen temperature, tympanic ear temperature, and then ear canal temperatures. Those are two separate ones. Tympanic goes clear down to the tympanic membrane, and the ear canal sensor doesn't go, it just sets in the ear canal. And then maybe a digestive tract sensor if we were looking at monogastric. So how do they compare, and how do we know which method we want to use? There's pluses and minuses to all of those. So here is the vaginal temperature, and I have the scale. This is vaginal temperature over 1 day. And I have the scale because you'll see as we go forward. Here's an ear canal temperature. So it's a little eye button that was stuck in the ear and then insulated from the outside temperature. The ear was wrapped up. So it doesn't do too bad, matching vaginal temperature. And we can collect that. Rumen temperature seems like an easy one to do because you can put the sensor in the rumen and just collect the data. So what is the disadvantage? Every time they go to drink, we lose our data. This was collected at every 15 minutes. The company was suggesting that we collect it every hour. If we collected every hour, I'm telling you, we wouldn't know what the data would be, how we should, or what data is good and what data is bad. So rumen temperature, while it seems very easy and very, very convenient, to me, it's hard to even manage animals based on rumen temperature. So now I'm going to give you another example of weight. Accuracy, precision, resolution of weight. How accurate can we measure a weight of an animal? How do we know how accurate we can measure? Do we look at the accuracy of the scale? I looked up scale accuracies last night, and I got them from plus or minus 1 pound. That's pretty good. and I found one that was plus or minus 0.2 pounds. That's amazing. But is that how accurate we can monitor weight in an animal? What impacts the error associated with weights? I talked to animal scientists, they're very concerned about gut fill, right? So we need to wait, we need to take them off a feed for so many hours so the gut fill is the same across the animals, right? But what else impacts the error of taking a weight measurement? I'm going to tell you that 1 pound scale, that isn't your error. Here's an example of a pig on a scale for 15 seconds. This is plus or minus 1 pound. The scale was calibrated. This is a pig that's pretty normal on the scale. We have ones that act a lot worse, and we have a few that act a little bit better. What do you think the range of weights is on that pig? And all the weights that were shown were accurate. So what I'm saying is if we walk a pig on the scale, capture a weight, walk the pig off the scale, we could have captured any one of these weights. Do I have a guess on what the range of weights are that we could get? 5 pounds. Anybody else guess? I have 7 pounds. So understand that when we're using images to do weight analysis, which we are doing, we try to get it very perfect. And we are very concerned about errors of 3 pounds. But understand that when we take our weights on our scale, we aren't more accurate than plus or minus 7 pounds on a finishing pig. So how do we expect our data from cameras to be better than plus or minus 7 pounds? And if anybody knows how to weigh a pig and eliminate that without hanging them on the rail, I am all interested. We have talked and talked and talked trying to figure out how to eliminate and get an exact weight of a pig, and we have not come up with a good way to do that. So the next topic, how am I doing on time-wise? Okay, so time syncing. So when we start collecting data from a lot of different data sources, and we need to be very, very careful on how we line up the data. So when we look at slow data collection, like we're looking at 1 minute, 15 minutes, 1 hour, and so most of those are physiological or weather parameter data that we're taking, and we try to line those up later and make some inferences. That is a reasonable thing to do. We can make sure that our times are synced at the beginning of our study, and every time we change sensors, we can verify, and we need to verify that all of our sensors are started by the same computer, or you're looking at the time on your phone, which is very accurate, and then syncing those times at the beginning. Small differences, if you're taking 1 minute data, small differences in time, a few seconds here or there, are not going to matter, right? Even a minute or two on body temperature isn't necessarily going to hurt your data. So this is data that was taken, and we're looking at dry bulb temperature and comparing it to respiration rate. So the respiration rate was taken twice a day by hand, and dry bulb temperature was recorded at the same time within a half hour. So those time syncs are fairly easy because we have a range of times we can work with. Respiration rate changes rapidly, but average respiration rate doesn't change all that fast. And our temperature can change rapidly, but not really rapidly. So when we start looking at body temperature, and we want to look at body temperature as it relates to maybe a standing activity. If we know the cow stood at say 1,800 hours, right? And we want to line that up. We really probably need to be within a minute or two to make sure that the reaction of body temperature is really associated with that behavior. But seriously, within 1 or 2 minutes, our time sinks are really not too big of an issue. When we start talking about fast data collection, faster than 1 hertz, and this is images, video, accelerometers, we need to sync those loggers at the beginning. That is very difficult because we need to sync on a millisecond level. And sometimes, however, that isn't quite enough. So we used accelerometers at 10 hertz and we captured video at 1 hertz. So we really need to be within a second. And this is a video, and you can see the sow standing up, and she stands up at about 1:30 or 1:29. And if you look at our accelerometer data, she stood up at 7 o'clock and 57 seconds, or yeah, 57 seconds. So we really need to line those up better if we really want to look at accelerometers and how they compare to behaviors. Now, the next topic is time drift. We don't even want to consider that the time that we set isn't going to be the time that we end with, right? So we have a study, we have 7 computers all working together to collect RFID and images. We only have one of those computers on the network. If anybody's worked with Windows, you understand why we don't want all those computers on the network. And if you don't work with Windows for data collection, I'll tell you, Windows automatic updates are killers. They will lose you data. You think you have them shut off, they are not shut off. So here's our setup. We have a depth sensing camera above a rack of RFID sensors. So when they come and drink, we capture 5 images. To eliminate or to understand how much time drift, there's our image. To understand that, we have a very long file name. And this is the location, this is the date and the time that the main computer that's hooked to the internet has, right? This is the image number, and then we have a series of RFID depending on where they are in the image. So here's the RFID. This is the timestamp from the computer that's collecting the images. After 1 month of data, we had one that was 2.5 minutes wrong, it's lagging, one, and then 2 that were over 4 minutes, and another one that was 2 minutes. So if you are doing multiple computers, there's a way you can set it up that you can have another computer that sends time out to everything, or you can then record it in your file name. So then you can go back and adjust if you need to adjust. In conclusion, we talked about accuracy, precision, and resolution, and why those are different and why they're important. We talked about, and then in ways that we should select our sensors. We have sampling frequency. We understand our sources of error, and it's not only the accuracy and precision and resolution, but the reality of taking data. And then I do have data, although I took it out, as understanding camera resolution and those impacts on measurement. So if anybody wants to talk to me at the break, we can talk more. And then I talked about time sync issues.